Today, I take on a topic that I think will come as a surprise to you. What we will learn is this: is that initial choice that we made about the unit of area measure, which was the square unit, that was far from inevitable. And we'll talk about another possibility today: the possibility of a circular unit, and with that, the possibility of an infinite number of choices at the start of the study of area will open up. Okay, so just a reminder here, and I'll build an analogy. The analogy will be to length. So, what does it mean to say that a segment is 12 meters long, for instance? It means that we have established a unit of length measurement, a unit of 1 meter, and then when we say that this particular segment is 12 meters in length, we mean that it is 12 of the unit. Okay, so in general, in the sciences, for instance, when we measure something, we always provide units at the end of it. So what we mean to say is that this is how many of the unit that we've established that we have. And so, of course, it would mean if we say that that segment is also 1,200 centimeters long, we mean to say that it contains 1,200 of the unit of 1 centimeter. And of course, we understand that there's no, excuse me, inconsistency between the 12 and the 1,200, as there might seem initially, because the units are different. We have 12 of 1 meter and 1,200 of 1 centimeter. And since those units are different, there's no contradiction between them. So, length conversion. This is part of the analogy that I wish to build as well. We know that we can convert from one unit to another when we measure in length. This is not something that we have done before because we haven't really been concerned with units of length measurement. At the very start of the class, when we talked about the concept of length, we said, well, of course, every length measurement will have some unit, but we'll just presuppose that and not actually state it, assume that it's centimeters or miles or whatever you like, but it didn't particularly make a difference at the time. But now, at this moment, since I wish us to consider the possibility of alternative systems of area measure, I do think we need to go back and take it seriously. So let's say that we had a length of 12 meters and we wish to convert that to feet. Well, obviously, we would make use of that basic equation that I looked up online that relates a foot to a meter. And one form of that is this, is that 1 foot is 0.3048 meters. And what I wish to do then is to use that equation to convert meters to feet. And how do we do that? Well, here's a way that I learned to do it that is really quite nice. So what we'll do is this, is we'll take that equation, 1 foot equals 0.3048 meters, we will turn it into a ratio, and we will turn it into a ratio such that meters will cancel out and only feet will remain after the conversion. Before I learned how to do this, I used to always worry about the conversions that I did. I knew that I would have to make use of some conversion constant, and I would have to multiply or divide by it, but I was often worried that I had done the wrong operation, that perhaps I should have divided when I multiplied, or I should have multiplied when I divided. So in this case, what we'll do is this, is we will multiply by a conversion ratio, and I will make sure to place meters on the bottom of that ratio so that meters will cancel and that unit of meters will not be left. So what then has to go on top? Well, feet, and we know that 1 foot is 0.3048 meters. Okay? And that, just understand that that ratio, the 1 foot over 0.3048 meters, since those lengths are equal to one another, that the value of that ratio is really 1. So all we've done is we've re-expressed the 12 meters. It's still the length that it was before, but now it would be expressed in feet. Okay, so of course I won't take the time to break out a calculator and to compute this, but here's what it would be. It would be 12 divided by 0.3048 feet. So we can be confident in this case the division what was required. So this is how one does unit conversion. And one could go the other way around as well. So let's say that we had 36 feet. How would we do the conversion? Well, let's construct a conversion ratio. The conversion ratio is such that feet will cancel. So I will place feet on the bottom of my ratio, which means that I must place meters on top. So it is then 0.3048 meters over 1 foot. And then the final answer will be 36 times 0.3048, and the unit is meters. So again, I could be confident that I have carried out the correct operation. I know in this case it must be multiplication by that constant 0.3048. Now, let's turn to area measure. and do what we did with length now with area measure. So when we began our study of area, we chose a particular unit of area measure. That unit was the unit square. That is the square of side length 1. And of course, that length of 1 for the side, that itself would have units, some length units, centimeters, feet, whatever it happens to be. We'll continue to not worry about that because at this moment in time, we're worried about the units of area measure. So let us just focus on that choice that we made. That is that we had a square of side length 1 as the unit of area measure. And then, of course, when we reported the area of a particular figure, what we meant to say is that that is the number of unit squares that it would take to fill the object, to cover the object without gap or overlap. Okay? So, for instance, if we were to have a rectangle with side lengths 2 meters and 7 meters, and let's say that our unit was a square of side length 1, then it would follow by definition that that particular figure had an area of 14 because it takes precisely 14 of that unit square to cover it without gap or overlap. And that was easy, right? I mean, rectangles are in general easy if the choice that we have made is the square unit. And then, as we learned in our study of the chapter, study of area in the chapter, once one has rectangles, it's easy to do parallelograms, and once one has parallelograms, it's easy to do triangles, and once one has triangles and parallelograms, it's easy to do trapezoids and so on. So our system, the derivation of area formulas for polygons, was a relatively simple matter. And really the reason that it was so simple is that we started with a certain kind of polygon, that is a square. Now, there was another possibility here. One that I probably said, or I mentioned that another possibility was there. Now let's talk in particular about what that is. The possibility is the circular unit. So let us henceforth no longer decree that our unit of area measure will be the unit square. Instead, let us decree that it will be the unit circle. And what is the unit circle? It is a circle of radius 1. And let's have symbolism to indicate, or a short abbreviation to indicate which unit of area measure we have chosen. And let us say that CU stands for circular unit, and SU, I don't know why that's SI, that should be SU, stands for square unit. So we now have circular units. And again, what that means is this, is that we will now measure in circular units, which means the question is always, how many circles of area 1 does it take to cover a figure without gap or overlap? So the unit circle. Oh, curious. The picture seems to be gone, so I will actually draw it. So here's a circle of radius 1. That's the unit circle. And let us measure area in that. Okay. Now, let us assume, so I guess I'll draw the pictures in. They seem to be gone. I don't know why Microsoft does this sometimes. So let us assume that the radius of each circle below is 1, and then we'll find the area of the total figure below. So it was something like this. So I'll create some circles. So here are some circles, here are some circles, here are some circles. Let's say they don't look like it, but let's say they all have radius 1. Well, what's the total area that's enclosed within this figure? Well, obviously, 1, 2, 3, 4, 5, 6, 7, 8. It's 8 total circular units. So a bit like the case of the rectangle, which is just, squares stuck together. That 2 by 7 rectangle was just 14 squares, unit squares stuck together. This is 8 unit circles stuck together. So trivially then, the area of this is 8 circular units. Now, what we want at this point is a formula that will allow us to go, that would allow us to give the area of a circle in circular units, okay? And to do this, I don't know that this is the right way, but it will work. To do this, let's go back to square units and consider what happens to a circle's area when we scale the radius by a factor of k. Okay? So let's see. I'm going to start with a circle that has, I'll start with a slightly better circle. So I'll start with a circle that has, let's say, a radius of, I'll just call it r, and let's say we scale it by some factor k. Okay. So we'll introduce some circle that I picture it as larger, though of course that's not inevitable. K could be less than 1, in which case it would be smaller, but I'll draw it larger. So we've scaled the circle, and let's talk about what happens to the area. Now, This is our first time to discuss in any depth at all the relationship between similarity and area, because of course when one scales by a scale factor, whatever it is, you produce a figure that is similar to the one that you had previously, and the question concerns what happens in this case to the area. So here it is, the start of our study of the relationship of similarity and area, which will be extended in the next section. So in square units, and I'll continue to use that unit here, the area of the original circle is pi r squared. So that's pi r squared square units. And then what's the area of the circle after we have squared, after we have scaled by the factor k? Well, it would be pi times kr squared, the entire quantity, k times r squared, square units. And the square of kr is k squared r squared. So there it is, k squared r squared. It's again square units. And then I'm going to rewrite this slightly, just rearrange. Write that as k squared times pi r squared, square units. And then compare that to the original, okay? So they both have that pi r squared in them, but notice that after the scale, we now have the k squared out front, okay? So here's what happened then. When we scaled the circle by the factor k, the area did not also grow by the factor k, it grew by the factor k squared. And that's actually a fundamental insight of great importance and power about the relationship of similarity and area. If we have two similar figures with the scale factor of k, the one is k squared times the area of the other. Okay? So there it is. The lesson is that when we scale a circle by the factor of k, the area scaled is k squared times what it was originally. And with this, we can derive the circle area formula for circular units. By definition, the area of a circle of radius 1 is 1 circular unit. That's just what circular units are. But the scale factor from a circle of radius 1 to a circle of radius r is obviously just r, right? Why do I multiply 1 by to get r? R. So what we did then is this, is we took a circle of radius 1 circular unit it contains, scaled it by a factor of r. Okay, so the area must be then r squared times what it was before, but it was 1 initially, so now it's 1 times r squared, which is r squared. So that right there is the area formula for a circle in circular units. It's simply r squared, okay? And perhaps then one will realize, hopefully one would realize that this would apply generally, even if we chose another kind of unit for area measure. We might, for instance, choose the equilateral triangle of side length 1, okay, as our unit of area measure, because, why not? And then when we report the area of a figure, that will mean how many equilateral triangles of side length 1 it takes to cover it without gap or overlap. And we would call that, of course, as triangular units, TUs. And then what would be the area formula for equilateral triangles in triangular units? It would just be side length squared, okay? So whatever the measurement is, side of a square, side length of an equilateral triangle, radius of a circle, or whatever you want, it's that squared that gives you the area formula in that particular unit of area measure. So the area of a circle of radius r is r squared in circular units. So if the radius is r, the area of this in circular units is simply r squared. So the analogy, I've already talked about that actually. The analogy is just this again. When we were in square units, the area of any square is sine squared. Now that we're in circular units, the area of any circle will be radius squared. There's a very close, tight analogy between the two. So let's do some examples. So a circle has radius 12, find its area in square and in circular units. Well, that pi r squared formula, that's for square units, okay? That's the context in which that was derived, and it's not the same area formula for circular units. So in square units, what do we get? So that would be 12 squared times pi, which is 144 pi. And again, that is square units. Now, what is it in circular units? Well, it's just simply 12 squared. 12 squared circular units, which is 144 circular units. So another way to put that, let's make sure you understand this, is that a circle of radius 12 contains the same area as 144 circles of radius 1. So let's say now, this should be, sorry, let me go back. Oops, too far. This should be number 2. Let us say now that a circle has an area of 36 circular units. Find its radius. Well, once again, in circular units, the area formula for a circle is simply radius squared. So that, of course, means the radius in this case has to be 6. So let's do a little unit conversion now. We could convert, as we saw previously, between, say, feet and meters, and we now can convert between also circular units and square units as well. And how do we do that? Well, we need an equation that relates a certain number of square units to a certain number of circular units, and that will allow us to construct ratios that will then allow us to do conversions. So let's just recap what we've done before. In square units, the area of a unit circle is, remember, a unit circle is a circle of radius 1, and in square units, that's pi times 1 squared, which is just pi. So how about the area of a unit circle in circular units? That, just by definition, is 1. How many unit circles does it take to cover a unit circle without gap or overlap? 1. It is what it is. So what that means is this, is that pi square units is equal to 1 circular unit, and that allows us to do conversions. So the area of a figure is 25 square units. So let us do the conversion to circular units. So how will this go? In precisely the way that we did conversions before. That is, we will start with the quantity that we wish to convert. So that is 25 square units, and we will multiply that by a conversion ratio. And we will place square units on bottom because we wish the square unit to cancel out. And we will put circular units on top. And what did we discover? That 1 circular unit is the same as pi square units. So what's the answer? 25 over pi circular units. Now let's go the other way around. So let us say that we have 49 circular units. How many square units is that? Well, multiply it by a conversion ratio. What's the conversion ratio? Well, let us place circular units on the bottom so that they will cancel out and leave only the square units that we have on top. And what we've found is that pi square units is equal to 1 circular unit. So this is 49 pi square units. So there it is. There's your introduction to circular units. And what should be clear at this point is that it is ultimately, from a mathematical point of view, arbitrary which system of area measure you choose, just as from a mathematical point of view, it's arbitrary whether you work in, say, feet or meters. And honestly, that's why I didn't really worry about units for length, because mathematically it doesn't really make a difference. In the sciences it might, but here it does not. And ultimately, the same will be true for area measure, that it doesn't matter which unit of area measure you choose. So for the most part, you don't worry about it. Most everybody does square units, and that's perfectly fine. But I did want you to understand that there is another possibility, because my typical experience here is that students just don't really realize that it is possible.